welcome to my podcast on Math 1220. Today we're going to be talking about Arclenth, okay? And my goal is to calculate the arc length of y equals x to the 3 halves power, where x ranges from 0 to 1, okay? Um, so let's just take a look at a little graph of this, okay? So the arc length here it's going to look something like that, okay? Or excuse me, that's the graph of the curve, okay? And if I could pull this tight, I'd like to be able to take this to a tape measure or a ruler and determine how long this curve is, okay? Um, we can't exactly do that, but instead, the idea here is to divide and conquer. Um, So let me just illustrate this to you, um, this idea, okay? And the idea is, hey, if I divide up this function into a small little chunk in x and a small little chunk in y, after all, the change in y, that length, that red length, representing change in y is the change in the function here, okay? With respect to a small change in x. Okay, then the length of this curve, L sub I, satisfies Pythagoras. L sub I is going to be the square root of delta y squared plus delta x squared. Okay, so the idea here is, hey, if I can break this into small little chunks along the curve, then I can get the exact length of the curve, okay? And here, delta x, that is the change in x, okay? That's the small change in x, okay? Another way of representing this formula for L sub I would be the square root of delta y over delta x squared plus 1 times by delta x. Okay, so there's a little algebra there. And the total length of the curve is then just going to be the sum of the little lengths. Okay. And I'm going to change this to be an approximation because as it's written, it is an approximation. Okay. Okay. If I want to get the exact length of the curve, well, instead of stopping at n inscriptions, what I'm going to do is I'm going to take infinitely many of them, but make sure that each inscription of the length is more precise. And just FYI, this length here, it's a straight line segment, so it's not exactly precise, doesn't exactly match the black length. It's off by just a little bit, okay? But it does a pretty good job. If I make delta x a little bit smaller and I have more inscriptions of these little lengths, I get a more precise answer. So if I want the most precise answer, I should take this limit as n goes to infinity in my step size for delta x, that is the number of little triangles that I inscribe, becomes infinite. And this will be the summation from I equals 1 to n of L sub I. But remember, I have a nice little formula for L sub I. And the nice little formula that I have is delta y over delta x squared. Hey, if I remember correctly, delta y over delta x, that's represented by f prime of x. So I square the derivative, I add 1 to it, and then I multiply by dx. Hey, I have a couple of things here that reminds me of calculus 1. This limit, the summation, and the delta x tell me that I could replace those three things by an integral. So that is, I would integrate from a to b on this integral. And I'm going to integrate the function here, f prime of x squared, add 1 to it, and instead of having delta x, I have dx. Okay. So now this becomes, this is exactly the formula for the arc length of a function. Okay. Okay. Now let's finish our example. So our goal was to find the length of the curve is to find the length of the curve f of x is x to the 3/2 for x between 0 and 1. Okay. So I just apply this formula. I think I'll need to know f prime of x. Okay. And f prime of x, we just bring the power down as we said we would. And this will be 3/2 times by x to the 1/2. Then we apply our formula that we just derived. So a is 0, b is 1. I'm going to get the square root of 3/2 times by x to the 1/2 squared plus 1. I'll then integrate with respect to x. Okay. Okay. Let's just clean this up. And we'll have 9/4 x plus 1 dx. Now, we can integrate this rather easily, and we'll just do a u substitution. U is everything inside the square root. Okay. So du over dx is going to be 9/4, and 4/9 times by du, that gives us dx. Okay. This will be this integral, and by the way, these limits were with respect to x, so this will become square root of u times by dx gets replaced by 4/9 times by du. And I'm going to change these limits of integration. We're going to change them to be with respect to u. So when x is 0, u is 1. When x is 1, u is 9/4 plus 1, which becomes 13/4. Okay. So let's anti-differentiate this. This will be u to the 3/2. I'll put the 4/9 out in front. From the exponent, we have to do 2/3. Okay. And then we're going to evaluate at u equals 1 and u equals 13/4. Okay. This will give us 8/27 times by u is going to be 13/4 to the 3/2 power minus u to the first u. When u equals 1, we raise it to the 3/2, and that just gives us 1. And this is our final answer. Okay. So that's great. I want to go through one more example and just mention a slight variant. So one of the key takeaways from today is this formula right here. That's the formula for the length of the arc of a curve. However, we can also use another formula for arc length. Okay. And this one is if you need to integrate with respect to y. So this would be y equals a to y equals b. And here you're going to have the derivative of x with respect to y squared. We're going to add 1, and we're going to multiply by dy. Okay. And let me just give you a little example of this. And our goal is to find the length of the curve x equals y squared from x equals 0, and excuse me, I got into my old habits. It's from y equals 0 to y equals 1. Okay? So here we just apply the formula. So this will be this integral from y equals 0, y equals 1, and we're going to have the square root. The derivative of x with respect to y is 2y. We're going to square that. We're going to add 1, and we integrate with respect to y. We clean this up. This is the integral from 0 to 1 of the square root of 1 plus 4y squared dy. Okay, well, how do we integrate this? This has a radical. So this is kind of telling us we're going to do a trigonometric substitution. And the trigonometric substitution we're going to do is y is equal to tangent. Okay. Now, we're going to have 1/2 times by tangent. Okay. And when we do that, this will become this integral from 0 to 1. Okay. And we're going to have the square root of 1 plus 4 times 1/2 times tangent of theta squared. And we're going to have to replace dy. dy becomes 1/2 times secant squared of theta d theta. So 1/2 secant squared of theta d theta. Inside this square root, we're going to have 1 plus tangent squared. That becomes this integral of secant of theta squared times by 1/2 times secant squared of theta d theta. Okay. Now, this becomes this integral from 0 to 1, and I'm pull out the 1/2. Okay. I pull out the 1/2, and we're going to get 1/2 times by secant cubed of theta d theta. Okay. Now we have to ask ourselves, how do we integrate this? And the answer is, we've seen this integral before, and I'm going to quote what that integral is. Okay. But just in case you didn't remember what this antiderivative is and how we'd calculate the antiderivative secant cubed, it would be an integration by parts. Okay. This is not one of the nice cases of secant, because secant is to an odd power, and that's the case that gets really difficult. Okay. So in class, I gave this antiderivative of secant cubed, and the antiderivative was going to be 1/2 is going to be secant of theta times by tangent of theta, okay, over 2 plus ln of secant of theta plus tangent of theta. Okay, and this was also multiplied by 1/2. Okay, so we also have limits of integration, and these are in terms of y equals 0 to y equals 1. Okay, so at the end of the day, we either have to back substitute, okay, and obtain what these would be, what these formulas would be in terms of y, okay, or we have to change these limits of integration to theta. Since I have previously put these limits of integration in terms of theta, I will back substitute so that you can see some variety. Okay. Now our substitution is y is equal to 1/2 tangent, so that says 2y over 1 is equal to tangent of theta. Okay. What this translates to in terms of a triangle is this. Here's angle theta. 2y is there. 1 is on the adjacent. This will be 1 plus 4y squared. Okay. So I'm going to rewrite this. Everything has a 2 in it inside this antiderivative, so it will be 1/4 times secant of theta. Secant of theta is nothing more than the hypotenuse here, so 1 plus 4y squared, multiplied by tangent, that's 2y, plus ln of this secant of theta, 1 plus 4y squared, plus 2y tangent of theta. Okay. Now we just need to plug in the values, and the values are y equals 0 and y equals 1. Okay. So we're going to do 1/4 times by, well, when y is 1, we'll have square root of 5 times by 2 plus this ln of square root of 5 plus 2. And when y equals 0, everything there is going to be 0. So I could do minus 0. Okay, but this is going to be our answer. This is the length of the curve. Notice it involved a trigonometric substitution, even an integration by parts that I hid a little bit because we've done this integral in class before. So some of these antiderivatives for arc length can get involved. They may involve trigonometric substitutions, and other times they'll involve various algebraic tricks. But the two key takeaways that I want you to know is I want you to know the formula for arc length, this is the main one when you integrate with respect to x, and also this one. So here I'll highlight it. Okay. So that formula for arc length and also this one. Okay. Okay, thank you for joining me. Bye.